Welcome to the deep dive. Today, we're going to be looking at reconfigurable intelligent surfaces.
RIS.
RIS, yeah.
Yeah.
Specifically, this paper, Global Optimal Closed-Form Solutions for Intelligent Surfaces with Mutual Coupling. Is mutual coupling detrimental or beneficial?
Yeah, this is a really cool paper. I think it kind of changes the way we think about designing and optimizing these surfaces.
Okay, so to start off, they use an analogy to help us understand how an RIS works. And it's familiar to, I think, anybody who's studied circuit theory, a multi-port network. Can you walk us through that?
Yeah, so they model the wireless channel as a network with multiple ports.
Okay.
And these ports represent the different elements, like the transmitter, receiver, and the RIS.
Okay.
And then to characterize this network, they use impedance and admittance matrices, which are denoted as Z and Y, respectively.
Okay, so those matrices are kind of like the blueprint that captures the relationships between all the different parts.
Exactly. Okay.
But they make a couple of simplifying assumptions to make the analysis a little bit easier.
Right.
The first one is the unilateral approximation.
Yeah, so that basically means that we're going to neglect the feedback channels.
Okay, so we're just looking at the main signal path. What's the second assumption?
The second assumption is perfectly matched antennas at both the transmitter and receiver.
Gotcha. Okay, so we've got our model and our assumptions. Now let's get into the heart of the matter. The paper explores two types of RIS architectures.
Right.
Fully connected and tree connected.
Right.
So let's start with the fully connected, which they also call BD-RIS or beyond diagonal.
Yeah.
So in a fully connected RS, every element on the surface is connected to all the others.
Yeah, that's right.
Okay, so it's like maximum flexibility.
Yeah, exactly. It gives you the most flexibility in how you can manipulate the signal.
But I'm assuming also maximum complexity.
Yeah, for sure. You get more flexibility, but it comes with a cost.
Okay, so their goal is to maximize the channel gain.
Right.
Which is basically how strong is the signal between the transmitter and receiver.
It's exactly. And they do this by finding a closed-form solution that involves diagonalizing the mutual coupling matrix. Right. Diagonalizing. Yeah. So you have this matrix, and diagonalization is a process of transforming that matrix into a simpler form where all the non-zero elements are along the diagonal.
Okay.
So it makes it much easier to work with.
Gotcha. So it's like if you have a big messy room and you organize everything so it's in its spot.
Exactly.
Okay. Now, how do they diagonalize that mutual coupling matrix?
So Proposition 1 in the paper kind of highlights a key property of the mutual coupling matrix that makes this possible.
Okay.
And essentially it states that for a reciprocal and lossy N-port network, the real parts of both the impedance matrix, Z, and the admittance matrix, Y, are positive semi-definite.
Positive semi-definite.
Yeah, so basically it guarantees that certain operations can be performed, like the diagonalization, without running into issues.
Okay, so it's like it's valid to do that mathematically.
Exactly.
Okay, so they use that property and they transform the optimization problem.
Right.
Okay.
And the outcome is that they find that the optimized, fully connected RIS achieves the theoretical upper bound on channel gain.
Okay.
So they squeezed out every last bit of performance.
Wow. Okay. Now, how does that happen?
So by diagonalizing the mutual coupling matrix, they're able to separate the optimization from the inherent properties of the channel.
Okay.
And the channel gain depends on both the channel itself and how the RIS is manipulating the signal.
Okay.
So they're able to isolate the RIS's contribution and optimize it independently.
Gotcha. Okay. And they prove this using the Cauchy-Schwarz inequality.
Yeah.
Okay. Now, stepping back a bit, the expression for that upper bound, I have a feeling it's got some insights packed in it.
Yeah, so it tells us that the maximum achievable channel gain depends on three main factors: the strength of the direct link between the transmitter and receiver, the scattering caused by the RIS structure itself, and the effectiveness of the channels between the transmitter, RIS, and receiver.
All right, so it's kind of like a recipe. You need all the parts to be good.
Yeah, exactly.
Now, where does mutual coupling come into this?
So mutual coupling actually affects the scattering caused by the structure of the RIS, and they show that when properly accounted for, it can actually enhance the scattering and contribute to a higher upper bound.
Okay, so mutual coupling, which we normally think of as a problem, can actually be a source of improvement.
Exactly, yeah.
Wow, that's really cool. Okay, so now we've explored the fully connected RIS, and we've seen how they derive this solution that achieves the upper bound. But fully connected architectures can be pretty complex.
Right.
So let's move on to the more practical tree-connected architecture.
Yeah, so they found that even with its simpler design, the tree-connected RIS also achieves that same upper bound on channel gain.
So we're getting like the same bang for our buck, but it's less complex.
Exactly.
Now, how do they prove that the tree-connected RIS is truly optimal, even with mutual coupling?
So the proof follows a similar structure to the fully connected case, but this time they focus on the admittance matrix Y instead of the impedance matrix.
Okay.
Because it's more naturally suited for analyzing the tree-like structure.
Gotcha.
And they essentially show that by carefully optimizing the phase shifts, they can achieve that same upper bound.
Wow, that's amazing. Okay, so now they're mentioning this tridiagonal RIS.
Yeah, so the tridiagonal RIS is just a special type of tree-connected RIS where each element is only connected to its immediate neighbors.
Okay.
And they show that despite this simplification, it can still achieve that same upper bound.
Wow. So it's like a simpler version of the tree.
Exactly.
With like a more linear connection.
Same.
There. Okay. This is all super interesting.
Yeah.
There's still more to unpack here.
Right.
But I think we can pick it up next time.
Sounds good. Yeah, so last time we were talking about how that tree-connected RIS can actually achieve the same performance as the fully connected one.
Yeah, it's pretty remarkable, like, how much we can get with a simpler design.
Exactly.
But I'm kind of curious to go beyond just, like, optimizing for specific configurations.
Right.
And think about, like, how the channel gain scales with the number of elements.
Right.
Because that seems like a pretty important consideration if we want to design, like, larger, more powerful systems.
Yeah, for sure. So that's where the channel gain scaling laws come in.
Okay.
So they make a couple of assumptions here. They assume that there's no direct link between the transmitter and receiver.
Okay.
So the signal's completely relying on the RIS.
Gotcha. So that it's like a worst case scenario, right?
Exactly, yeah.
Cool.
And then they also model the channels as Rayleigh fading, which is just a common way to represent the randomness of the wireless signals.
Right.
And so they find that as the number of RIS elements increases, the channel gain also increases. But the rate of increase depends on whether you consider mutual coupling or not.
Okay.
So they basically have two different scaling laws.
Okay.
One with mutual coupling and one without.
Okay. So it like fundamentally changes the behavior.
Yeah, exactly.
Okay. So what do those scaling laws look like?
So in the case without mutual coupling, the scaling law is pretty simple.
Okay.
Basically, the average channel gain increases linearly with the number of elements.
Okay, so it makes sense.
Yeah, more elements, more gain.
Yeah.
But when you introduce mutual coupling, it gets a bit more complicated.
Okay.
The average channel gain still increases with the number of elements.
Okay.
But the rate of increase is it's influenced by the structure of the mutual coupling matrix.
Okay, so like the way that the elements are interacting with each other really plays a role.
Exactly.
Yeah.
It's not just more is better.
Right.
You have to carefully consider the mutual coupling.
Now, this kind of goes back to the title of the paper.
Right.
Is mutual coupling a friend or foe?
Yeah, so they find that when the mutual coupling is properly accounted for in the optimization,
Okay.
it actually improves the average channel gain.
Really?
Yeah.
So it's like it's not bad.
It's not inherently bad. It's just how you use it.
Wow. Okay.
So they did simulations to validate this.
Okay, so they wanted to make sure it wasn't just theoretical.
Right, yeah.
They actually like put it to the test.
Yeah, so they modeled a realistic RIS
Okay.
as a UPA
Okay.
of dipole antennas.
Okay.
And they carefully selected the dimensions of the array and the spacing between the elements to make sure that the mutual coupling effects were captured accurately.
Okay, so they were very like specific in their modeling.
Yeah, they were very thorough. And then for modeling the mutual coupling, they used a formula to calculate the impedance between two dipole antennas.
Okay.
It's a well-established formula.
Okay.
And so it makes sure that the simulation is really reflecting what's going on in the real world.
Gotcha. It's physically grounded.
Exactly. Yeah.
And what about the channel? Did they model it the same way?
Yeah. So they use the same assumptions as the theoretical analysis.
Okay.
So they assumed that there was no direct link and that the channels were Rayleigh fading.
Okay.
So everything was consistent.
Gotcha.
And so, yeah, the simulations confirmed that both fully connected and tree-connected RISs, when they're optimized with these proposed solutions,
Okay.
they achieve the upper bound on channel gain.
Okay.
So their theory is actually backed up by real simulations.
That's great. So it actually works.
Yeah.
Now, did they look at different levels of mutual coupling?
Yeah, so they looked at how the channel gain changed as they adjusted the spacing between the elements.
Okay.
And they found that stronger mutual coupling, when it's properly accounted for, actually led to even higher channel gain.
So the more mutual coupling, the better.
As long as you're optimizing for it.
Okay, so you have to be smart about it.
Exactly.
But it's like, it's not a bad thing inherently.
Right, right.
Wow, okay.
And then they also looked at the performance of BD-RIS versus D-RIS.
Okay.
So BD-RIS is the beyond diagonal.
Right.
And D-RIS is the conventional or diagonal.
Okay.
And they found that BD-RIS consistently outperforms D-RIS.
Okay.
And so when they're both optimized with awareness of mutual coupling, BD-RIS gives you about a 2D dB gain.
Okay.
And that's actually consistent with what they saw when they were looking at BD-RIS without mutual coupling.
Gotcha. So it's better, like across the board.
Right. Okay.
Now, what happens when you introduce mutual coupling?
So when you introduce mutual coupling, the performance gap between BD-RIS and D-RIS, it actually increases.
Okay, so the stronger the mutual coupling,
the better BD-RIS performs.
The better BD-RIS.
Yeah.
Wow. Okay, so it's like it's really able to like take advantage of that.
Exactly.
Wow. Okay, so to kind of summarize, the simulation showed that both types of RIS can achieve that theoretical upper bound.
Right.
When they're optimized correctly, they also showed that stronger mutual coupling, when it's used the right way, actually makes things better.
Yeah.
And then finally, BD-RIS is always better than D-RIS.
Right.
Especially when there's strong mutual coupling.
Exactly.
Okay. I think that's a pretty good summary.
Yeah, that's pretty much it.
This is really, really interesting research. I think it's got a lot of implications for the future of like wireless technology.
Yeah, for sure.
So maybe we can talk about that next time.
Yeah, that sounds good.
Okay, so we've seen from those simulations that mutual coupling can actually be a good thing.
Right.
But now I kind of want to dig into like the mathematical analysis. Like how did that actually happen?
So they set up a scenario to analyze where there's no direct link between the transmitter and the receiver.
Okay.
So the signal has to go through the RIS.
Okay.
And then they model the channel again as Rayleigh fading.
Okay.
And so they basically compare the average channel gain with mutual coupling, which they denote as eMIMC2.
Okay.
And the average channel gain without mutual coupling, which is E nu MC2.
Okay. And they're taking the average over many different like realizations of the channel.
Exactly.
So they're not just looking at like one specific instance.
Right.
Okay. Now those expressions look pretty complicated.
Yeah, but they really boil down to the channel characteristics and the mutual coupling matrix.
Okay.
And without mutual coupling, it actually simplifies a lot because the mutual coupling matrix is just a diagonal matrix.
Okay, so it's like each element is only influenced by itself.
Exactly.
Yeah, all right.
But when you add the mutual coupling in, it gets a lot more complicated because now the matrix is showing all these interactions. So how do you actually compare these two?
Yeah, it seems like it would be a big mathematical mess.
Yeah, so they focus on specific terms within those expressions.
Okay.
And they find that the expression for the average channel gain with mutual coupling is actually dominated by these two terms, TR and TR1.
Okay, so TR, is that like trace?
Yes, that's the trace.
Okay, and what's that squiggly Z?
So that's the real part of the mutual coupling matrix, ZI.
Okay, so those are the key players in this analysis.
Right.
Okay. Now, to understand their significance, they introduced two lemmas.
Okay. So the first lemma basically states that for a positive definite matrix, the trace of its inverse is always greater than or equal to this specific value.
Okay.
That's related to the diagonal elements of the original matrix.
So it's like the trace of the inverse, like there's a lower bound?
Exactly.
Yeah.
And then the second lemma says that the trace of the squared inverse is also bounded below by a similar value. So you can kind of think of it as there's a certain level of robustness in the connections that you can't go below. And using these two lemmas, they're able to prove a proposition.
Okay.
which basically states that the average channel gain with mutual coupling
Okay.
is always greater than or equal to the average channel gain without mutual coupling.
Right. So they've proven that like mutual coupling is always better.
Or at least as good.
Okay.
But there's a caveat here. This is only true if you're optimizing the RIS while considering the mutual coupling.
Okay, so you can't just ignore it.
You have to take it into account.
Gotcha. You have to like actually optimize for it.
Right.
Okay, so then they do simulations to validate these findings, right?
Yeah, so they again use a very realistic setup.
Okay.
They model the RIS as a UPA of dipole antennas, and they're very careful about the dimensions and spacing.
Okay.
And they use that same impedance formula to calculate the mutual coupling.
Okay.
And they use the same assumptions about the channel.
Okay.
And so what they find is that the simulations actually confirm their theoretical results.
Okay.
Both fully connected and tree-connected RISs achieve that upper bound.
Wow. So their math actually like holds up in a practical setting.
Exactly, yeah.
That's incredible.
Yeah.
Now they also look at different levels of mutual coupling. Right?
Yeah, so they change the spacing between the elements to change the amount of mutual coupling. And what they find is that stronger mutual coupling actually leads to even higher channel gain.
So the more mutual coupling, the better.
As long as you're optimizing for it correctly.
Okay, so it's not like a bad thing in and of itself.
Right.
It's just you have to know how to use it.
Yeah, you have to be smart about it.
Okay. Now going back to BD-RIS versus D-RIS.
Yeah, so they compare those two again.
Okay.
And they find that BD-RIS always outperforms D-RIS.
Right.
And when they're both optimized with mutual coupling awareness,
Okay.
BD-RIS gives you about a 2 dB gain over D-RIS.
Okay, and we saw that before, right?
Yeah, that was the same as without mutual coupling.
Okay. Now, does that gap change when there's mutual coupling involved?
Yeah, so as the mutual coupling gets stronger,
Right.
the performance gap between BD-RIS and D-RIS actually gets wider.
Oh, wow. Okay, so it's almost like BD-RIS is able to use the mutual coupling to its advantage.
Exactly.
Whereas D-RIS can't really do that as well. Okay, so I think I've got like the main takeaways here. The simulation showed that both types of RIS can reach that upper bound.
Yeah.
They showed that stronger mutual coupling is actually a good thing when you optimize for it.
Right.
And they show that BD-RIS is always better than D-RIS.
Yeah.
Especially when the mutual coupling is strong.
Exactly.
Okay. This has been an amazing deep dive. I feel like we've learned so much
Yeah, me too.
about RIS and mutual coupling.
That's a really interesting topic.
Yeah. It really challenges like how we think about these systems.
For sure.
And yeah, I think that this research has a lot of potential to really change the way we design wireless communication.
Yeah, I think so too.
And to our listeners, thank you so much for joining us. We hope you enjoyed this exploration of RIS and mutual coupling. We'll see you next time on The Deep Dive. Welcome back, everyone. Today we're taking a deep dive into the world of BD-RIS.
BD-RIS.
Yeah, Beyond Diagonal Reconfigurable Intelligent Surfaces. Catchy, right?
Well, it's certainly descriptive.
It is. It's all about how we can manipulate electromagnetic signals to make wireless communication even better.
So we're talking about basically surfaces with interconnected elements that can do more than just reflect signals. They can actually guide them too.
Exactly. And this deep dive is all about a research paper that's asking a pretty key question. Is mutual coupling between those elements a good thing or a bad thing?
Mutual coupling, huh? That's where things can get interesting.
Definitely. Get ready for some pretty heavy math. We're talking eigenvalues, impedance matrices, even the Lyapunov central limit theorem. Don't worry, we'll break it all down.
Sounds like a challenge.
It is, but it's worth it, trust me. This paper is all about finding the best possible ways to configure these BD-RIS systems.
So optimizing their performance?
Exactly. They're specifically looking at two types of BD-RIS, fully connected and tree connected. And the goal is to max out that channel gain.
Channel gain.
Yep, make that signal as strong as it can be.
Gotcha. So more power to the signal, basically.
You got it. So the paper kicks off by using multi-port network theory to model the BD-RIS system.
Multi-port networks. That sounds familiar.
Well, it's basically a way to describe electrical circuits with multiple inputs and outputs. And they compare two ways to represent it: Z parameters and Y parameters.
Z parameters for impedance, Y parameters for admittance, right?
Right on. Think of it like two different languages for describing the same electrical circuit. Now, to make things a bit easier, they make a couple of assumptions.
Assumptions, always got to have those in research.
Right. So first, they ignore any feedback channels.
So no signals bouncing back from the receiver to the transmitter?
Nope. They call this the unilateral approximation. It works well when things are far apart.
Makes sense. What's the other assumption?
Perfectly matched antennas at both ends, the transmitter and receiver.
So no signal reflections there.
Exactly. Everything's tuned perfectly for efficient power transfer. With those assumptions in place, they start digging into the nitty-gritty of fully connected RIS.
Fully connected, meaning every element is connected to every other element.
Exactly, like a big web of interactions. They want to see how to maximize channel gain with this setup while accounting for mutual coupling.
And they're assuming a lossless and reciprocal RIS, right?
You got it. No energy wasted, and signals travel the same in both directions.
So how do they tackle this optimization problem? It sounds pretty complex.
Well, they start with the Z parameters, and they do something clever. They diagonalize the mutual coupling matrix, ZI.
Diagonalize? What does that do?
It basically simplifies the matrix, makes it easier to work with mathematically.
Ah, so they're transforming it into a more manageable form.
Exactly. And this allows them to use a solution that already exists for simpler systems, ones without mutual coupling.
Clever. They're building on previous work to solve a new problem.
Exactly. And through this process, they stumble upon a key insight they call Proposition 1.
Proposition 1. All right, lay it on me.
It says that for any reciprocal and lossy N-port network.
N-port network, that's just our multi-port circuit with a specific number of ports.
You know it. The real parts of both the impedance matrix, Z, and the admittance matrix, Y, are positive semi-definite.
Positive semi-definite sounds like a mouthful.
It is, but basically it means that the power used by the network is never negative.
Which makes sense, physically speaking. Can't have negative power.
Right. It's like a mathematical check to make sure our model is grounded in reality.
Like a sanity check. I like it.
Yeah.
So Proposition 1 is basically saying our model isn't breaking the laws of physics.
Exactly. And they use this property to figure out the maximum possible channel gain.
The theoretical limit for signal strength, even with mutual coupling in the mix.
Exactly. And the cool thing is, this limit isn't just an abstract formula.
It has a real-world meaning.
It does. It relates to the direct link strength between the transmitter and receiver, how the RIS scatters signals, and the strengths of the channels between the different parts of the system.
So the math is telling us something concrete about how the system behaves.
Right on. So that covers fully connected RIS, but what about tree-connected RIS? Remember we talked about it being less complex.
Yeah, less connections between the elements, kind of like a branching structure.
Exactly. So how do they approach the optimization for this one? Do they still stick with the Z parameters?
I'm curious about that too. It seems like they'd need a different approach.
Well, they actually switched to Y parameters for tree-connected RIS.
Yeah, parameters. So now they're working with admittance instead of impedance.
Right. Turns out the constraints of the tree-like structure are easier to handle with the admittance matrix, YII. But the goal remains the same, maximize that channel gain while dealing with mutual coupling.
So same goal, different tools for the job. Makes sense. Do they still go through that diagonalization process like they did with the fully connected RIS?
They do. But it's tailored to the specific shape of the tree-connected RIS.
So the diagonalization process is different because the connections are different.
Exactly. To make it clear, they focus on a type of tree-connected RIS called a tri-diagonal RIS. Imagine each element only connected to its neighbors on either side.
Okay, so a simpler connection pattern, I can picture that.
Oh, they use an auxiliary variable and a bunch of math tricks to diagonalize the admittance matrix, YII in this case.
So they adapt the diagonalization process to fit the tridiagonal structure.
Exactly. And this allows them to use a pre-existing solution for optimizing RIS without mutual coupling, just like before. It's all about building on what we already know.
I'm noticing a theme here. They're really good at leveraging existing knowledge to tackle these new challenges.
And what's the main takeaway from all of this tree-connected RIS analysis? Does it perform as well as the fully connected one, even with mutual coupling? I'm on the edge of my seat.
Well, get ready for a surprise. Their analysis shows that even with fewer connections, the tree-connected RIS can actually achieve the same maximum channel gain as the fully connected one, even with mutual coupling.
No way. That's amazing. So we can potentially simplify the design without sacrificing performance.
Exactly. Tree-connected RIS seems to hit a sweet spot, high performance without all the complexity. To prove this point, they do the math and show that the expression for channel gain in the tree-connected case is the same as the upper limit they found for the fully connected case. This gives solid mathematical backing to the idea that tree-connected RIS can be just as effective even with mutual coupling present.
That is absolutely incredible. It really opens up possibilities for simpler, more cost-effective BD-RIS systems.
I agree. It's exciting to see how theoretical analysis can lead to such practical implications.
So we've covered how to optimize both fully connected and tree-connected RIS, and even touched on the idea of channel gain scaling laws. What's next on our deep dive agenda?
Next, we'll delve deeper into those scaling laws and explore how the channel gain behaves with and without mutual coupling. This will give us a clearer picture of how much mutual coupling really impacts the performance of these RIS systems.
Sounds like things are about to get even more interesting. I can't wait.
So to really get a handle on how mutual coupling messes with the scaling of channel gain, the researchers decided to focus on a specific scenario.
Okay, what kind of scenario are we talking about?
One where the direct link between the transmitter and receiver is completely blocked.
So they're basically saying, let's see how much we can boost the signal just by using the RIS and its fancy wave manipulation?
Exactly. They want to isolate the effect of the RIS itself. To refine their analysis even further, they assume that the channels connecting the transmitter and receiver to the RIS,
Those are ZIT and ZRI, right?
yeah, got it, have entries that are independently and identically distributed according to a Rayleigh distribution.
Ah, the Rayleigh distribution.
Yeah.
Classic for wireless environments, right?
Right.
Lots of scattering and reflection going on.
Exactly. It captures how signals can fade in those complex environments. Think about when you walk behind a building and your cell phone signal weakens.
Yeah, that's partly because of how those signals are scattering and fading according to that Rayleigh distribution.
Right on. For this analysis, they decided to go with the z-parameters representation, but they assure us that the same conclusions would hold if they used the y-parameters instead.
So the choice of representation doesn't really change the big picture.
Nope, the insights stay the same.
Okay, that makes sense. So walk me through how they derive the scaling law with mutual coupling in the mix.
Well, they begin with that expression we saw earlier for the achievable channel gain with mutual coupling.
Okay, I vaguely remember that one. Lots of symbols.
Right. And since they are assuming that direct link is blocked, they simply set the ZRT term to 0.
Makes sense. So they're just focusing on the RIS contribution.
Precisely. Then, to understand how this channel gain behaves on average, they take its expectation.
Expectation, meaning the average value over many different realizations of those random channels.
You got it. But this involves some pretty heavy math. We're talking expectations of products and squares of those random channel variables.
I can imagine. Didn't they have to make some approximations to handle those tricky calculations?
They did, actually. A couple of key approximations, but they are well justified, and they validated them later on through simulations.
Simulations are always a good reality check. So what were these approximations?
First, they treated the random variable ZRIUZ1ZIT as being uncorrelated with the squared norms of those other channel terms.
Okay, so they're assuming a certain kind of independence between different parts of the channel.
Yeah, think of it as those different parts acting independently of each other.
Makes sense. Especially when the number of RIS elements starts to get large, right?
Exactly. The more elements you have, the more reasonable that assumption becomes. It really simplifies the expectation calculations.
Okay, so what was the second approximation they made?
This one relies on the concept of channel hardening.
Channel hardening. I feel like I've heard that before. Isn't that something that happens in massive MIMO systems?
You are exactly right. As you increase the number of antennas in a system, the fluctuations in the channel start to average out. It becomes more stable, more predictable.
So the channel hardens. Interesting. But are they applying this idea to the RIS scenario? I mean, an RIS might not have a massive number of elements.
That's exactly what they're doing. They argue that as the number of RIS elements increases, even if it's not massive, the squared norms of certain channel terms start to behave more like deterministic quantities.
Deterministic meaning not random anymore.
Pretty much. Their variance decreases significantly. So for a sufficiently large RIS, they can essentially treat those squared norms as if they're fixed values.
Okay, I see. So another simplification to make the analysis more tractable.
Right. And by applying these approximations and using some powerful math tools,
Math tools
like the Lyapunov central limit theorem, for instance, they end up with a very elegant expression for the scaling law of the average channel gain, all while taking mutual coupling into account.
Okay, spill the beans. What does this scaling law look like?
It's surprisingly concise. The average channel gain with mutual coupling, which we denote as EMC2, is proportional to the product of the channel gains of ZRI and ZIT.
So stronger individual channels lead to a stronger overall gain. That makes intuitive sense.
It does. And they use the symbols RI and RIT to represent those channel gains, but it doesn't stop there. The scaling law also depends on two specific traces related to the mutual coupling matrix, ZII.
Traces. Remind me what those are again.
The trace of a matrix is just the sum of its diagonal elements.
Right. So these traces are essentially measuring some key characteristics of that mutual coupling matrix that influence how the channel gain scales.
Exactly. It's a combination of the individual channel strengths and the structure of the mutual coupling that determines the overall scaling behavior.
Okay, that makes sense. Now, for comparison, they also derive the scaling law for the average channel gain without mutual coupling.
Right. So in this case, the RIS elements are only affected by potential impedance mismatching.
Impedance mismatching. That's when the antennas on the RIS aren't perfectly tuned to the transmission line, right? Leading to signal reflections and reduced efficiency.
You nailed it. And in the simpler case, the mutual coupling matrix, ZII, becomes a diagonal matrix.
Diagonal meaning all the off-diagonal elements are zero.
Exactly. And each diagonal entry just represents the self-impedance of the corresponding RIS element. So how does this simplification affect the scaling law?
That's a good question.
They go through a similar process, taking expectations, applying approximations, and they find that the scaling law in this case is proportional to the product of the channel gains, OTI, the number of RIS elements, NI, and the real part of the RIS antenna self-impedance, ZI.
Okay, let me try to summarize this. Both scaling laws depend on those individual channel gains, but the one with mutual coupling involves those traces of the mutual coupling matrix, while the one without it relies on the number of elements and the antenna self-impedance.
Excellent summary. It really highlights how mutual coupling adds a whole new layer of complexity to how the channel gains scales.
It does. But there's also a neat connection between the two scaling laws, right?
Absolutely. You can actually view the scaling law without mutual coupling as a special case of the one with mutual coupling. If you imagine that mutual coupling matrix being a simple diagonal matrix with the same self-impedance value all along the diagonal,
then the two scaling laws become equivalent.
Exactly. The general case with mutual coupling encompasses that simpler case without it. It's quite elegant, really.
I agree. It's a nice way to connect the two scenarios. So even though they used some approximations to derive these scaling laws, they showed through simulations that they were surprisingly accurate, even for a realistic number of RIS elements. That's reassuring.
Simulations are always a good way to test those theoretical predictions. So we've got these scaling laws, and we've seen how they capture the impact of mutual coupling. But the million-dollar question remains.
Is mutual coupling a friend or a foe?
That's the question the researchers tackle head-on in the next part of their analysis. They compare those scaling laws with and without mutual coupling to see if this phenomenon ultimately helps or hurts the performance of these RIS systems.
Ooh, the suspense is killing me. I can't wait to see what they find.
Huh.
All right, so we've been on the edge of our seats waiting to find out. Is mutual coupling a friend or foe? How did the researchers settle this debate with those scaling laws?
Well, they dug into those mathematical details, focusing on the parts of the scaling laws that were different, specifically those traces of the mutual coupling matrix in the scaling law that includes the coupling.
Those traces, if I recall correctly, are basically a measure of how strongly the RIS elements are interacting with each other.
You got it. The bigger those traces, the stronger those mutual coupling effects are. So to figure out if mutual coupling is a good thing, they needed to figure out how those traces influence the scaling of that channel gain.
Okay, so it all comes down to those traces. How did they analyze their impact?
Well, they brought in two mathematical lemmas.
Lemmas?
Yeah, think of them as helper theorems. They provide some key insights into those trace terms.
Lemmas, theorems, proofs. Sounds like we're going deep into the world of mathematical reasoning.
We are. So lemma 1 states that for any positive definite matrix, and we know that the real part of our mutual coupling matrix fits the bill, the trace of its inverse is always greater than or equal to a certain value related to its diagonal elements.
Okay, so that sets a lower bound for that trace term. What does lemma 2 tell us?
Lemma 2 takes it a step further and shows that the trace of the squared inverse of that positive definite matrix, it's also bounded from below.
So both lemmas are basically putting constraints on how small those trace terms can get.
Exactly. And with these lemmas in their toolkit, they unveil the main result, which they call Proposition 2.
Proposition 2. This must be the answer to the mutual coupling mystery.
It is. Proposition 2 says that under the specific conditions they outlined, remember those independent and identically distributed Rayleigh fading channels, mutual coupling between the RIS elements actually improves the average channel gain.
Wow, really? So all those interactions between the elements are actually a good thing?
On average, yes. The mathematical proof, which leans heavily on those lemmas, shows that the scaling law with mutual coupling always produces a higher average channel gain than the scaling law without it.
That is incredible. Mutual coupling, a secret weapon for BD-RIS. But hold on, if mutual coupling is so beneficial, why was it often considered a problem in earlier research on RIS?
That's a great question, and it highlights a really important nuance. Proposition 2 tells us that mutual coupling is beneficial on average. However, for any specific instance of those random channels, mutual coupling could either help or hurt the channel game. It's not a guaranteed win every time, but in the long run, it's an advantage.
So it's not a sure thing in every single case, but overall it's a plus.
Exactly. And this really underscores why it is so important to develop those optimization algorithms that are aware of and can actually take advantage of mutual coupling.
If we just ignore it, we could miss out on those performance gains.
Precisely. Now, are there any caveats to Proposition 2? Does it apply to all types of RIS?
Well, it's important to note that this result is specifically talking about fully connected and tree-connected RISs that are optimized with mutual coupling in mind. It doesn't really tell us anything about what happens with those simpler diagonal RISs in the presence of mutual coupling.
So there's still more to explore, especially when it comes to those less complex diagonal RIS architectures?
Absolutely. This paper opens up a whole new avenue for research. We need to rethink how we design and optimize these RIS systems to harness the power of mutual coupling.
Couldn't agree more.
Well, this deep dive has been absolutely mind-blowing. My whole perspective on BD-RIS, the power of mutual coupling, has completely changed.
It's a perfect example of how theoretical analysis can lead to some pretty surprising discoveries and open doors for technological advancement.
And I have a feeling this is just the beginning of the BD-RIS story. I'm eager to see what future research unveils about this interplay between mutual coupling and RIS performance.
The future of wireless communication is looking bright, and I think BD-RIS, with its unique ability to leverage mutual coupling, will play a key role in shaping it.
Well, that concludes our deep dive into the world of BD-RIS and the unexpected benefits of mutual coupling. Thanks for joining us. Welcome back, everyone, for another deep dive. Today, we're going beyond diagonal with RIS.
RIS, always a hot topic.
It really is. We've talked about those amazing reconfigurable intelligent surfaces before, but usually we're looking at those typical setups, where each element just does its own thing.
Right. Like a bunch of independent antennas on a surface.
Exactly. Each one can adjust the phase of a signal,
Yeah.
but they're not really talking to each other.
No, not really interacting, just kind of doing their own phase shifting.
But what if, and here's where it gets really interesting, what if they could actually work together?
Now we're talking. That's where beyond diagonal RIS comes in, right?
You got it. And that's what we're diving into today. We're going beyond diagonal to explore architectures where those little antennas on the surface can actually interact and cooperate.
And that opens up a whole new world of possibilities. We could have much more precise control over wireless signals.
Definitely more control, like shaping and directing signals in ways we could only dream of before.
This paper we're looking at today really dives into the nitty-gritty of all this. It's called Global Optimal Closed-Form Solutions for Intelligent Surfaces with Mutual Coupling. Is mutual coupling detrimental or beneficial?
Catchy title. So mutual coupling. Sounds kind of technical.
Yeah, it's one of those terms that might make your eyes glaze over.
But I have a feeling it's pretty important for this whole beyond diagonal RIS thing.
It's absolutely key. Mutual coupling basically means that the elements in an antenna array, like those little antennas on our RIS, are actually influencing each other.
They're not just independent actors anymore.
Nope. Think of it like this. When one antenna sends out a signal, it can affect how the neighboring antennas are behaving.
So they're all kind of intertwined.
Yeah.
Interesting. But hasn't mutual coupling always been seen as kind of a problem? Something to avoid?
You're right. Traditionally, engineers have tried to minimize mutual coupling. It can mess things up if you're not careful. But this paper flips that idea on its head.
Flipping the script, huh?
They're saying that if you understand mutual coupling and account for it properly, it can actually be a good thing.
Wow, a secret weapon almost.
Exactly. Instead of fighting against it, you can actually harness it to improve the performance of your RIS.
That's pretty mind-blowing. So how do they actually do that? How do they make mutual coupling work for them instead of against them?
Well, they start with a really solid model of the whole system. They use something called multi-port network theory to represent everything: the transmitter, the receiver, and the RIS itself.
I vaguely remember that from my circuits class. Does it involve lots of ports and signals bouncing around?
You got it. The whole system is treated like a network with multiple ports. Each element on the RIS acts like one of those ports.
So each tiny antenna is its own little port. Makes sense.
And this whole network can be described mathematically using matrices. Specifically, they use something called an impedance matrix, which is denoted by Z, or an admittance matrix, which is denoted by Y.
Ah, matrices. I remember those. They're those grids of numbers that can be a bit intimidating, but they hold a lot of information.
Exactly. These matrices tell you how the whole system is connected and how signals flow through it.
So they're not just random numbers. They actually represent the real-world physics of how the antennas are interacting.
Right. And what's really important is that these matrices capture the mutual coupling between the elements.
So it's all in there, all those intricate interactions between the antennas.
And by carefully analyzing those matrices, you can get a much deeper understanding of how the entire system behaves, including all the effects of mutual coupling.
Okay, I'm following so far. So we've got our multi-port network model, we've got our impedance and admittance matrices, but how do we actually use this to make our RIS better?
That's where the real cleverness of this paper comes in.
Okay, spill the beans.
They use this model to find what's called the optimal configuration of the RIS.
Optimal configuration.
It means finding the best possible settings for all those little antennas to maximize something called the channel gain.
Channel gain. That's basically a measure of how strong the signal is at the receiver, right?
Exactly. You want to make that signal as strong as possible. So the authors of this paper figured out how to tweak all those antenna settings, taking into account all the mutual coupling effects to achieve the maximum possible channel gain.
Wow, so they're basically optimizing the whole system for maximum performance. That's impressive.
And they do this for two different types of RIS architectures. One is called fully connected, and the other is called tree connected. And this is where the choice between the Z matrix and the Y matrix gets interesting.
Okay, so different architectures, different matrices. I'm curious to hear more about that. Why the distinction?
So fully connected RIS, that's like the ultimate in flexibility. Every single element on the surface can be connected to every other element.
Wow, a total free-for-all? Sounds powerful, but also maybe a bit chaotic to manage.
It is complex, lots of interconnections to keep track of, and that's why the Z matrix works well here. It naturally captures all those intricate relationships in a fully connected system.
Makes sense. It's all about impedances, right? So how about the tree-connected RIS? You mentioned it was less complex.
Yeah, tree-connected RIS is more structured. The connections between elements form a kind of branching pattern, like a tree.
I can picture that. Fewer connections overall, which probably makes it easier to handle in practice.
Right, and it turns out that the Y matrix, which is based on admittances, is a better fit for describing the signal flow in this kind of setup.
Okay, so we've got our model's Z matrix for fully connected, Y matrix for tree connected. But how do we actually use these to find the best possible RIS configuration?
Well, for fully connected, they start with this goal of maximizing channel gain. Mathematically, they're trying to find the reactance matrix, denoted as SI, that achieves this maximal
Reactance matrix that rings a bell from circuits.
Yeah.
It's all about how much the circuit resists changes in current, right?
Yep, that's it. And they use the Z parameter model because it directly captures the reactances of this fully connected structure.
Okay, makes sense. So where does mutual coupling fit into all this? How do they actually incorporate it into their optimization process?
This is where it gets really elegant. They introduce what's called an auxiliary variable. It's denoted by XII, and it allows them to transform the impedance matrix into a much simpler form.
A simpler form. That sounds promising.
It is. Essentially, this transformation kind of diagonalizes the problem, making it look like a system without mutual coupling.
Ah, so they're taking a complex problem and making it look like a simpler one that we already know how to solve.
Yeah,
That's clever.
exactly. And that allows them to leverage a solution from another paper that deals specifically with systems without mutual coupling. They apply that solution to their transformed problem, and through some mathematical magic, they arrive at a formula for the optimal reactance matrix, HDI, that maximizes channel gain even with all the mutual coupling going on.
Wow, that's amazing. So they're not just brute forcing a solution, they're using some pretty sophisticated math to find the absolute best configuration.
Pretty elegant. And they actually prove that this solution is globally optimal. You literally cannot get any better performance than what they've achieved.
That's impressive. So they've cracked the code for fully connected RIS. What about tree connected? How do they find the optimal setup there?
The approach is similar in spirit, but tailored to the tree structure. They're still trying to maximize channel gain, but this time they use the Y parameter model because it's a better fit for this architecture.
Right, right. So do they use another auxiliary variable here as well?
You bet. They introduce a new variable, BI, to transform the admittance matrix into something easier to work with. And again, they leverage a previously proposed solution that works for a simpler scenario.
It's like they're building upon existing knowledge, adapting those solutions to this new world of mutual coupling.
Exactly. They're not reinventing the wheel. They're recognizing the underlying mathematical structure and finding ways to apply those existing tools to this new challenge.
That's a great point. It highlights the importance of building on previous research and finding those connections across different areas. But let's talk about performance for a second. We said earlier that tree-connected RIS is simpler, maybe less flexible than fully connected. Does that mean it can't achieve the same level of performance?
That's what's remarkable. Even with its simpler structure, when you optimize a tree-connected RIS with mutual coupling in mind, it can actually achieve the same channel gain upper bound as the fully connected RIS.
Hold on, so you're telling me that I can get the same top-notch performance with a design that's potentially much easier and cheaper to implement?
You got it. That's why tree-connected RIS is such a strong contender for real-world applications. It's a beautiful example of how understanding and exploiting the underlying physics, in this case mutual coupling, can lead to innovative and practical solutions.
Okay, I'm really starting to see the potential here. But you mentioned scaling laws earlier. Can you remind me what those are and how they fit into this whole picture?
Sure. Scaling laws basically tell you how the performance of a system changes as you scale it up. Specifically, how does the performance change as we add more and more elements to our RIS?
So it's like a formula that tells us how much better things get as we make our RIS bigger and more complex.
That's the basic idea. The authors of this paper actually derived these scaling laws for both fully connected and tree-connected RIS with and without considering mutual coupling.
So we can actually predict how much gain we'll get as we build larger and more sophisticated RIS systems. That's pretty powerful.
It is, and those scaling laws also reveal some fundamental differences between systems that account for mutual coupling and those that don't. For example, with mutual coupling, the scaling law depends on the specific characteristics of the mutual coupling matrix.
Mutual coupling matrix, that's the one that captures all those interactions between elements, right?
Exactly. And the scaling law without mutual coupling, it's much more straightforward. It mainly depends on the self-impedance of the elements and how many there are.
Okay, I'm starting to appreciate the mathematical depth here. It feels like we're really unlocking a new level of control over wireless signals, almost like we're learning to speak their language. But before we get too carried away, what's the next step in our deep dive? Where do we go from here?
Well, we've talked a lot about the intuition behind mutual coupling. Now let's dive into the heart of the paper and see how the authors mathematically prove that mutual coupling can actually boost performance.
Okay, now we're getting into the nitty-gritty. Sounds like it'll be a fun ride.
It's all about clever inequalities, lemmas, and some really elegant mathematical reasoning. We'll break it down step by step so everyone can follow along.
Awesome. Can't wait to see the math behind the magic. Okay, so we've explored all the theoretical stuff, and we saw how those simulations really back up the idea that mutual coupling can be a good thing. But I think it's time to zoom out a bit. What does all this really mean? What's the big takeaway for the future of wireless communication?
That's the key question, right? We don't want to just get lost in the equations. This paper has some serious real-world implications.
So how could these findings actually change things out there in the wild?
Well, first of all, it's a huge win for tree-connected RIS. We saw that it can actually achieve the same performance as fully connected RIS.
But it's way easier to implement.
Exactly. Less complex, more cost-effective. That means it's much more likely to be adopted in real-world scenarios.
So we could actually see this technology out there in our homes, offices, cities, not just a theoretical concept.
Absolutely. Tree-connected RIS strikes that perfect balance between performance and practicality.
Got it. So point one, tree-connected RIS is a winner. What else?
The second big takeaway is the importance of mutual coupling-aware optimization. We can't just ignore those interactions between elements.
Because if we do, we're leaving performance on the table, right?
Exactly. Those simulations showed us that pretty clearly. If you want to get the most out of BD-RIS, you have to design and optimize with mutual coupling in mind.
So embrace the coupling, don't fight it.
Right. And that means developing new algorithms and techniques that can handle that complexity.
Okay, so 2 big points. Tree-connected architectures and mutual coupling-aware design. What else should we be thinking about as we move forward with this technology?
Well, this paper focused mainly on maximizing channel gain.
Which is super important, of course.
Of course. But there are other things we can do with BD-RIS, other ways we can leverage mutual coupling.
Like what? Give me some examples.
Well, think about beamforming, for instance. We could potentially use mutual coupling to create highly focused beams that target specific areas.
So instead of just boosting the overall signal, we could actually shape and direct it with much more precision.
Exactly. That could lead to more reliable connections, longer range, even new types of communication.
This is really exciting and feels like BD-RIS could revolutionize how we use wireless technology.
Yeah.
What are you most excited about when you think about the future of this stuff?
What gets me most excited is the idea of creating truly intelligent wireless environments. Places where we can adapt and optimize the way signals behave in real time.
Almost like we're creating a wireless ecosystem that can respond to our needs.
Yes. And this paper, with its rigorous analysis and those surprising results, is a big step in that direction. It's showing us what's possible when we start thinking differently about how wireless signals work.
I'm definitely on board. This has been a fantastic deep dive. Big thanks to the authors of this paper for really pushing the boundaries.
I agree. It's a great example of how different fields can come together: electromagnetics, signal processing, optimization, to create something truly groundbreaking.
All right, listeners, that wraps up our exploration of BD-RIS and mutual coupling. We hope you found it as fascinating as we did.
If you're hungry for more, be sure to check out the paper yourself. And keep exploring the world of wireless technology. There's always something new to discover.
Until next time, stay curious. Welcome to a deep dive that kind of flips the script on reconfigurable intelligent surfaces, or RIS for short.
Yeah.
We're going to explore how something that's usually a performance killer,
Right.
mutual coupling, that interference between elements, can actually be like a secret weapon.
It's a fascinating area,
Yeah.
especially when we move beyond the typical diagonal RIS configurations into the realm of beyond diagonal, or BD-RIS,
BD-RIS, okay.
where elements are interconnected for greater flexibility.
Exactly. And our source material for this deep dive is a paper titled Global Optimal Closed-Form Solutions for Intelligent Surfaces with Mutual Coupling. Is mutual coupling detrimental or beneficial? Gets pretty deep into the mathematical weeds, but don't worry.
Yeah.
But we'll make sure to pull out the insights that matter most for you.
Absolutely. The paper starts off by setting the stage,
Right.
reminding us of the limitations of conventional diagonal RIS, where each element acts independently,
Right.
and this limits the control you have over the signal.
Yeah, it's like having a bunch of light switches that can only be fully on or off.
Yeah.
No dimming allowed.
Exactly.
BD-RIS, with its interconnected elements, changes that.
Yes.
And the paper focuses on 2 types.
Okay.
Fully connected, where every element is linked, and tree connected,
Right.
which strikes a balance between complexity and performance.
Think of fully connected as having direct flights between every city.
Oh, okay.
Amazing connectivity,
Yeah.
but potentially chaotic.
Yeah.
Tree connected is more like a hub and spoke system.
Okay.
Streamlined,
Right.
but you might have a layover.
I like that analogy. That's great.
Yeah.
Now, where this paper really stands out is how it tackles mutual coupling.
Yeah,
Most research tries to just sweep it under the rug because it makes the math so much harder.
exactly. They dive right in,
Yeah.
using multi-port network theory to model the whole system.
Okay.
Each element of the RIS becomes a port in this network.
Gotcha.
And the mutual coupling is represented by impedance and admittance matrices, Z and Y, respectively.
Okay, time for a quick refresh. For those who hasn't brushed up on their multi-port network theory lately,
Yes.
what are these matrices actually telling us?
So imagine the Z matrix as a map of all the electrical relationships between elements. Each entry in the matrix captures the impedance, the resistance to the flow of signals between a pair of elements. Mutual coupling shows up as non-zero values off the main diagonal.
So it's like a social network diagram, but instead of friendships, we're mapping electrical interactions.
Exactly.
The stronger the mutual coupling between two elements, the bigger the number in their corresponding matrix entry.
Exactly. And the Y matrix is like the flip side of the coin, representing admittances. It's easier to use when analyzing systems with specific connection patterns, like our tree-connected RIS.
Gotcha. Now, the authors set out to find the best possible way to configure the RIS.
Yes.
They want to maximize the channel gain.
Right.
In simple terms, what does that mean and why should we care?
Channel gain basically tells us how strong the received signal is. Maximizing it means getting the clearest signal possible, which translates to better performance, faster data rates, wider coverage, and so on.
So we're aiming for that crystal clear call quality.
Exactly.
In our wireless communication.
Yeah.
Okay, makes sense.
Yeah.
Now let's get into the meat of their approach, starting with fully connected RIS. They talk about diagonalizing the impedance matrix. Break that down for me.
It's a clever mathematical technique that lets them transform the messy, fully connected impedance matrix into a simpler diagonal form.
Gotcha.
This makes the optimization problem much easier to tackle.
So it's like tidying up a tangled mess of wires so you can actually trace individual connections.
Exactly.
But how do they actually do this diagonalization? There's an equation involved, right?
Yes. They define a new variable xi, which is essentially a transformed version of the reactance matrix xi. Representing the RIS configuration. The equation is xii equals z naught times the real part of zi to the -1/2 times the quantity xci plus the imaginary part of zi times the real part of zi again to the -1/2.
All right, let's unpack that.
Sure.
Z naught is the characteristic impedance. Like the baseline resistance of the system.
Exactly.
Then we have the real part of zi, capturing energy dissipation. What about the imaginary part of Z?
That's the imaginary part of the impedance matrix, representing energy storage. They're essentially breaking down the impedance matrix into its core components and then using them to define this new variable xi.
So this transformation allows them to leverage their previous work.
Yes.
Which didn't include mutual coupling to solve this more complex scenario.
Exactly.
But how do we know this new solution is any good? How do they show it's the best possible configuration for the RIS?
They prove it's optimal by deriving a channel gain upper bound, the absolute maximum channel gain you can theoretically achieve in the system. And guess what? Their solution actually hits this upper bound.
Oh, wow. That's impressive.
Yeah.
Can we take a look at the equation for this upper bound?
Yeah.
It's denoted as the magnitude of h star squared, right?
Yes. Here's the equation.
The
magnitude of h star squared equals the quantity, the magnitude of h to t plus the norm of si squared times the norm of at squared. All squared.
All right, let's break it down.
Sure.
We've got SHIRI and SIT. What are these terms and how do they relate to our system?
They're transformed versions of the original transmission impedances. Think of them as describing the signal paths between the transmitter-receiver and RIS. SRT is the direct path. SRI is transmitter to RIS. And SIT is RIS to receiver.
So the upper bound equation says that the maximum channel gain happens when you combine the strength of these individual paths in the most efficient way.
Exactly.
And their solution achieves that, proving it's the best you can do.
Exactly.
Wow.
Remember, this is all for a fully connected RIS,
right,
which is complex to build.
Yeah.
What about the tree-connected architecture, which offers a simpler approach?
Right.
Let's explore that next.
Sounds good. Let's see if they can achieve similar results with a less complex setup onto the tree-connected RIS.
So we've seen how the researchers cracked the code for optimizing fully connected RIS, even with mutual coupling in the mix.
Right.
Now the question is, can they achieve similar magic with the simpler tree-connected architecture?
Right. The tree-connected RIS is like a well-organized network with branches, offering a balance between performance and complexity. But does this simpler structure limit its potential?
That's what the paper dives into next.
Okay.
And it's where the admittance matrix or Y matrix comes into play.
Yeah.
Remember how we said it's better suited for analyzing systems with specific connection patterns?
Yes. It's like using a specialized map to navigate a complex maze instead of a generic map that shows everything.
Yeah.
So how do they use the Y matrix to tackle the optimization problem for the tree-connected RIS?
Their goal is still the same,
Okay.
maximize channel gain.
Right.
But instead of tweaking the reactance matrix, XEI, they're now working with the susceptance matrix, BI.
Okay.
This matrix represents how easily signals can flow through the RIS elements.
Gotcha.
And it needs to be optimized while taking into account the specific connections of the tree-connected architecture.
Okay, so they're switching gears to susceptance instead of reactance.
Exactly.
Working within the admittance domain.
Yes.
But they still need to account for mutual coupling, right?
Absolutely.
Do they use a similar diagonalization trick?
Absolutely.
Okay.
They want to transform the problem into a form.
That resembles the no mutual coupling scenario, so they can apply their existing solutions.
Okay.
They define a new variable BI,
Right.
which is a transformed version of the susceptance matrix BI,
Right.
taking into account the admittance matrix of the RIS-YI.
Okay.
Yeah.
And I bet the equation looks pretty similar
You're right on the mark.
to the one they used for XI in the fully connected case.
Here's the equation for BI.
Okay.
BI equals Y naught times the real part of YI to the -1/2 times the quantity BI plus the imaginary part of YI
Right.
times the real part of YII again to the -1/2.
It's almost identical.
Exactly.
Except they've swapped out ZI with YI
Yeah.
and Z naught with Y naught,
Right.
reflecting the switch to the admittance domain.
Yes.
Okay, this transformation allows them to simplify the problem and apply their existing optimization tools.
Exactly.
And then they use an algorithm specifically designed for tree-connected RIS
Yes.
to find the optimal susceptance matrix BI.
This algorithm takes into account the limited connectivity of the tree structure, ensuring a solution that is both efficient and practical.
Yes.
So they've managed to optimize both fully connected and tree-connected RIS, accounting for mutual coupling in each case.
Exactly.
But here's the real nail-biter. Can this simpler tree-connected architecture actually achieve the same level of performance as the fully connected one?
That's where things get really interesting.
Okay.
The paper demonstrates that, surprisingly, even with its simpler structure, the tree-connected RIS can reach the same channel gain upper bound
Really?
as the fully connected RIS.
Hold on. That's a game changer.
Yeah.
It means you don't need the super complex fully connected setup to get the maximum performance benefit.
Exactly.
Wow, this could have huge implications for real-world RIS deployment.
Absolutely.
But how do they prove this mathematically?
They revisit the same channel gain upper bound equation we saw earlier. The magnitude of H star squared equals the quantity, the magnitude, SCRT, plus the norm of SRI squared times the norm of SAT squared, all squared.
Right.
But this time, they substitute the scattering parameters, SCRI and SCRT, with their admittance domain equivalents.
Okay.
Derived from the Y matrix.
So they're essentially translating the language of the upper bound equation from impedance to admittance, aligning it with the tree-connected architecture.
Precisely.
Okay.
They then derive a condition based on these admittance domain scattering parameters that must be satisfied to achieve the upper bound.
Okay.
This condition involves a phase term phi RT and normalized versions of the scattering parameters denoted as a CII and SET.
So this condition ensures they're squeezing every ounce of performance out of the system.
Exactly.
But how do they connect this condition to the actual susceptance matrix BI of the tree-connected RIS?
They manipulate the equation for the scattering matrix theta bar, which is expressed in terms of B through a series of clever mathematical maneuvers.
Right.
They arrive at a system of linear equations in complex coefficients.
Okay.
This system connects BI to a set of new variables, alpha and beta, derived from the scattering parameters.
So it's like they've cracked a secret code.
Exactly.
Translating between the language of scattering parameters and the language of the susceptance matrix.
Precisely.
But how do they actually solve this system of equations? So it sounds pretty complex.
They ingeniously demonstrate that this system of equations, despite its apparent complexity, has a unique solution.
Okay.
And they can find the solution using a specific algorithm designed for tree-connected RIS.
Right.
Based on their previous work.
So they've built upon their existing mathematical toolbox.
Exactly.
Adapting their solutions to tackle this new challenge.
Right.
By solving this system of equations, they find the optimal susceptance matrix, BI,
Yes.
that achieves the channel gain upper bound, proving that even the tree-connected RIS can deliver maximum performance in the presence of mutual coupling.
Exactly.
That's amazing.
It's a powerful demonstration of how careful mathematical analysis can lead to surprising and impactful results.
Absolutely. But so far we've been talking about achieving specific channel gain values.
Right.
How does this translate to the overall performance of the system as the number of elements in the RIS increases?
That's a great question.
It's like understanding how the performance of a choir changes as you add more singers.
Yeah.
Does it simply get louder?
Right.
Or does the quality of the sound change as well?
Exactly.
What do the researchers have to say about this?
To address this, they delve into the concept of scaling laws, which describe how the performance of a system changes as you scale up the number of elements. In this case, they want to understand how the average channel gain changes as you add more elements to the RIS, both with and without mutual coupling.
So they're looking at the big picture, the overall trend, instead of focusing on individual data points.
Exactly.
Okay.
Yeah.
But they specifically analyze Rayleigh fading channels.
Right.
Why focus on this particular type of channel?
Rayleigh fading is a widely used model for wireless channels, where the signal experiences multiple reflections and scattering, like echoes in a canyon. It's a good starting point for theoretical analysis.
Right.
And the insights gained from studying this model can often be generalized to other more complex channel models.
Okay, so it's a simplified version of reality that helps them grasp the fundamental behavior of the system.
Right.
Okay, how do they go about deriving these scaling laws? It sounds like a mathematically challenging task.
It does involve some intricate calculations, but we can break down the key ideas. They start by analyzing the average channel gain achievable with mutual coupling. Using the expression for the channel gain upper bound the magnitude of h star squared as their foundation.
So they're building upon their previous work again.
Yeah.
But this time they're not interested in a specific channel gain value.
Right.
They want to understand how the average value changes as you add more elements to the RIS.
Exactly.
How do they actually calculate this average?
They take the expectation of the channel gain upper bound expression.
Okay.
Essentially, they're averaging over all possible channel realizations. Considering the randomness inherent in wireless channels, to see what the typical channel gain would be for a given number of RIS elements.
It's like simulating thousands of different scenarios.
Exactly.
To see how the system performs on average, considering the unpredictable nature of wireless signals.
Yeah.
But the equation for the channel gain upper bound is pretty complex.
Yes.
How do they manage to calculate its expectation?
They break down the equation into individual terms and analyze the expectation of each term separately.
Gotcha.
They use some clever approximations, such as assuming that certain random variables are uncorrelated, to simplify the analysis.
It's like simplifying a complex recipe by substituting readily available ingredients without compromising the overall flavor.
Exactly.
Can you give me a concrete example of one of the terms they analyzed and how they calculate its expectation?
One of the key terms they examine is the magnitude of ZRI times the real part of ZII to the -1 times Z at t all squared.
Okay, so this term captures a specific signal path through the system.
Right.
Considering the influence of mutual coupling,
yes.
How do they find its average value?
They cleverly employ properties of the trace operator, a mathematical tool from linear algebra, and utilize the fact that ZRI and ZIT are independent, Rayleigh distributed random variables. This means their values follow a specific probability distribution, often used to model fading in wireless channels.
So they're bringing in statistical tools to tackle the randomness of wireless channels.
Exactly. Through careful manipulation, they derive a closed-form expression. For the expectation of this term, this expression depends on the channel gains, representing the strength of the signal paths and the trace of the inverse of the real part as JDI, capturing the impact of mutual coupling.
So it's like they've distilled a complex interaction into a concise mathematical formula.
Exactly.
Okay, and they repeat this process for each term in the channel gain upper bound equation,
Precisely.
It's a meticulous process. But they managed to derive a complete expression for the scaling law of the average channel gain with mutual coupling.
Yes.
Wow. This expression is a function of the channels gains the impedance matrix and, importantly, the number of RIS elements.
Correct.
So this scaling law tells them how the average channel gain changes as they add more and more elements to the RIS, considering the effect of mutual coupling.
Right.
But they also analyze the case without mutual coupling for comparison, right?
Yes. To understand how much mutual coupling influences performance,
Right.
they need a baseline for comparison. Yeah. So they derive a separate scaling law for the average channel gain when mutual coupling is absent. In this simpler case, the impedance matrix is diagonal, making the analysis more straightforward.
It's like conducting a control experiment where they remove one variable, the mutual coupling, to isolate its effect.
Exactly.
What does this scaling law without mutual coupling look like?
Right.
Is it drastically different from the one with mutual coupling?
At first glance, the two scaling laws appear quite different.
Okay.
The scaling law without mutual coupling primarily depends on the channel gains,
Uh-huh.
the self-impedance of the RIS elements, and the number of elements.
Okay.
It lacks the complex trace terms that appear in the scaling law with mutual coupling,
Right.
suggesting that mutual coupling introduces a new level of complexity to the system's behavior.
So it seems like mutual coupling really does change the game, at least mathematically.
Yes.
But can you give me a more intuitive understanding of how these two scaling laws differ?
Right.
How do they tell us whether mutual coupling is ultimately helpful or harmful?
That's the crux of the matter, and that's what they analyze in the next section.
Okay.
They go beyond just deriving the scaling laws. They actually compare them to see whether mutual coupling, when properly accounted for, can actually improve the overall performance of the system.
Okay, the suspense is building.
Yes.
Does mutual coupling end up being the villain or the unexpected hero of the story?
Right.
Let's dive into their analysis and find out. All right, so we've been on this mathematical journey exploring scaling laws with and without mutual coupling.
Right.
Now, for the big reveal,
Okay.
is mutual coupling friend or foe?
This is where the paper flips the script.
Okay.
They found that under certain conditions, mutual coupling actually enhances the average channel gain.
Wow.
It's a bit of a shocker considering we usually try to minimize it.
It's like discovering that a bit of friction, usually seen as a hindrance, can actually help you grip a surface better.
Exactly.
But how do they back this up mathematically? How do they compare those scaling laws to prove mutual coupling's unexpected benefit?
They introduced two powerful mathematical tools,
Okay.
Lemma 1 and Lemma 2.
Okay.
These lemmas establish inequalities related to the trace of the inverse of positive definite matrices.
Okay.
And remember, the real part of the impedance matrix is positive definite.
Right, so they're using these lemmas to essentially set boundaries on specific terms within the scaling law equations.
Exactly.
What's the significance of these inequalities?
These inequalities enable a direct comparison between the scaling law with mutual coupling and the one without. By applying the lemmas, they demonstrate that the scaling law that accounts for mutual coupling is always greater than or equal to the scaling law that ignores it.
So they've mathematically proven that when you optimize the system correctly, incorporating mutual coupling can actually lead to higher average channel gains.
Exactly.
Wow, this changes the entire game for RIS design.
It really does.
Instead of viewing mutual coupling as an obstacle, we can potentially harness it to boost performance.
Yes.
This has significant implications for the future of RIS technology.
Absolutely.
It's like finding a hidden treasure where you least expect it.
Exactly.
But this is all based on theoretical analysis.
Right.
Did they put these ideas to the test in the real world?
Absolutely.
Okay.
They conducted extensive simulations to validate their findings, and the results are impressive.
Right.
Their simulations confirmed that both fully connected and tree-connected RIS, when optimized using their proposed solutions, achieve the predicted channel, gain upper bound, even when the channels exhibit more complex fading characteristics than the simple Rayleigh model.
So the simulations solidly back their theoretical findings.
Yes.
That's reassuring. What were some of the key observations from those simulations?
Okay.
What did they actually see happening?
One striking observation was that stronger mutual coupling, resulting from closer element spacing on the RIS, actually led to higher channel gain.
Really?
This really underscores the idea that mutual coupling, when properly managed, can be a valuable asset.
Wow.
Rather than a liability.
It's counterintuitive, but exciting. What else did their simulations reveal?
They also compared their mutual coupling-aware optimization approach with traditional methods that ignore mutual coupling.
Right.
The results were quite stark.
Yeah.
The systems optimized without considering mutual coupling suffered a significant performance drop,
What?
sometimes as much as 5 dB.
Wow.
Particularly when the elements were closely spaced.
So not only did they demonstrate the potential benefits of incorporating mutual coupling,
Right.
but they also highlighted the potential pitfalls of neglecting it.
Exactly.
This makes a strong case for adopting their approach.
It does.
It's been an incredible journey unpacking this research. We've gone from understanding BD-RIS and the complexities of mutual coupling to uncovering the surprising advantage it can offer when we account for it in the design process. And it leaves us with a thought-provoking question.
Yeah.
If mutual coupling, something typically seen as detrimental, can be beneficial, what other hidden opportunities might we uncover in the intricate world of wireless communications?
That's a great question.
It is, and that's something for all of our listeners out there to ponder as we continue to explore and push the boundaries of technology.
Absolutely.
For our listeners who want to delve deeper into the mathematical intricacies of this research, I highly encourage you to check out the full paper. You won't be disappointed. Until next time, keep those minds curious and keep diving deep. Welcome back, everyone, to the Deep Dive. Today we're going deep on BD-RIS, Beyond Diagonal Reconfigurable Intelligent Surfaces.
Yeah.
Which is pretty cutting-edge wireless communication tech.
Absolutely. It's a fascinating area.
Now, to set the stage for everyone, can you give us a quick rundown of what a BD-RIS actually is?
Sure. So basically a BD-RIS is a surface, right? But it's not just any surface. It's covered in all these interconnected elements. And these elements, they can actually manipulate electromagnetic signals.
Ooh.
Yeah. So it's like having a surface that can shape and direct wireless signals.
So instead of just our typical, antennas, it's got this whole surface that's actively
controlling the signals.
Wow. Okay, so that's the BD-RIS. Now, I understand there's some debate surrounding something called mutual coupling in these systems.
Yes, mutual coupling. That's the big question.
Right.
It's essentially the electromagnetic interaction between the elements on the RIS.
Okay.
You see, people often see it as a problem because it can distort the signals.
Right.
But the research we're diving into today, it kind of suggests that we might actually be able to use this mutual coupling to our advantage.
Oh, interesting. So it's not necessarily a bad thing.
It might not be. That's what's so exciting.
Okay, so how do they even begin to approach this idea of mutual coupling in this research?
Well, they start with a simple scenario, right? Just a single antenna transmitter talking to a single antenna receiver. And they communicate through the BD-RIS.
Okay.
And to represent the wireless channel, they use a multi-port network model.
So they're isolating the effects of the BD-RIS.
Exactly, trying to keep things controlled.
Okay, makes sense. Now, what kind of BD-RIS are we talking about here?
So they focus on two main types. The first is fully connected, where every single element is connected to every other element.
Okay, so maximum control, but maybe more complex.
You got it.
Gotcha.
And then there's tree connected, which has a simpler, more efficient design.
So a trade-off between control and complexity.
Finding that sweet spot.
Okay, I'm following. Now, how do they represent these systems mathematically? It must get pretty complex.
Well, for the fully connected RIS, they use something called impedance matrices.
Okay.
They're denoted as Z parameters.
Z parameters, are you?
And for the tree-connected RIS, they use admittance matrices, or Y parameters.
Impedance and admittance. That takes me back to my circuit analysis days.
Yeah.
Can you just remind me how those concepts apply here?
Sure. So the impedance matrix, Z, it basically describes the relationship between the voltage and the current at each port of the network.
Okay.
So it tells us how the system behaves as a whole.
Gotcha.
Now, equation 1 in the paper shows us how this matrix is structured.
Okay, I see. They've broken it down into these submatrices representing different parts of the system.
Right. You've got ZIT, which represents the interaction between the transmitter and the RIS. Then you have ZRI, that's for the RIS receiver link.
Okay.
And ZRT represents the direct path between the transmitter and the receiver.
Okay.
That we're assuming is blocked for our analysis.
To simplify things, right?
Exactly.
So ZI, that would describe the interactions between the RIS elements themselves.
Right. That's where the mutual coupling comes in.
Uh-huh.
And equation 2 shows how they use these Z parameters to actually calculate the channel.
Which is essentially describing how the signal moves from transmitter to receiver, right?
Exactly, like the path it takes.
Okay, and the Y parameters, are those just an alternative way to represent the same thing?
Exactly. It's like using admittance instead of impedance. It's like looking at the same object from different angles.
I see, I see.
Equations 3, 4, and 5 define the admittance matrix Y and all its submatrices.
Okay.
And they mirror the structure of the impedance matrix.
All right, so they're similar in structure.
Yes, just different perspectives.
Got it. And then equation 6 gives us the channel, but this time in terms of the Y parameters.
Right, which is more convenient for analyzing the tree-connected RIS.
Makes sense. Now, the whole point of this research, the goal, is to maximize what they call channel gain, right? Essentially making the signal as strong as possible at the receiver.
You got it.
And this is where the optimization problem comes into play, right?
Exactly.
Okay, so how do they go about optimizing these systems, especially with this whole mutual coupling thing to consider?
Well, they formulate these optimization problems, separate ones for the fully connected and the tree-connected RIS.
Okay.
And the aim is to find the settings that will give us the maximum channel gain.
Makes sense. So let's start with the fully connected case.
Yeah.
How do they set up the problem mathematically?
Okay, so equation 7 in the paper, it shows the optimization problem for that fully connected RIS. And they're trying to maximize the square of the magnitude of the channel.
Which represents the channel gain.
Exactly.
Okay, and I see they have some constraints listed there in equation 8.
Right, those constraints are important.
Yeah.
They make sure that the solution we get is actually physically possible.
So don't be some theoretical thing.
Exactly. It has to work in the real world.
Gotcha. Yeah. But I can imagine that solving this optimization problem directly, it could get pretty messy, right?
Oh, absolutely.
With all those interactions between the elements.
It's a lot to handle.
Yeah.
So they introduced this clever trick.
Okay.
They diagonalize the impedance matrix, ZEI.
So they're basically simplifying the problem.
Yeah, making it easier to work with.
Gotcha.
They define a new variable, XII, shown in equation 9.
Okay.
And with this new variable, the problem becomes a bit more manageable.
All right, so they've simplified things. What's the next step?
Well, now they need to connect this transformed problem to an existing solution from some previous research.
Okay.
And to do that, they have to switch from the Z parameter representation to the S parameter representation.
Right, because the previous research used S parameters.
Exactly.
So it's like translating from one language to another.
Precisely. And they have to do this while preserving the meaning, of course.
Of course.
Equation 17 and 18. They define the S parameters based on the transformed Z parameters.
Okay, I see.
Then they introduce this new variable in equation 19, which is related to XI. And this allows them to express the optimization problem in its final form, shown in equations 20 and 21.
Using the S parameters and this.
Yes, and this final form lets them directly apply a known solution from that earlier research.
Oh, that's clever.
It is. They can find the optimal, which they denote as S.
Okay, and once they have that, they can work their way back to find the optimal S, right?
Exactly, using equations 19 and 10.
It's like a 3-step process.
Yeah.
Transform, optimize, then transform back.
You got it.
Pretty neat. But how can they be sure that this solution is truly the best possible solution?
That's where the concept of a channel gain upper bound comes in.
Okay.
They show that their solution actually achieves this upper bound.
So it's as good as it gets, theoretically.
Precisely. They've mathematically proven it's optimal.
That's reassuring. So they've tackled the fully connected case. What about the tree-connected RIS? How do they approach that?
For that one, they turn to the Y parameter representation. It's better suited for this type of structure.
Okay, makes sense.
Equation 28 lays out the optimization problem, which, as you might expect, also aims to maximize that channel gain.
Right. That's the ultimate goal.
Exactly.
And just like in the fully connected case, they've got some constraints in equation 29 to make sure the solution is physically realizable.
Right. Always got to keep it real.
Yes. I see they've specifically highlighted the connectivity pattern of a tree-connected RIS, where each element is directly connected only to its neighbors.
Exactly.
So no long-distance connections.
Not in this case.
Interesting. So how do they tackle this optimization problem? Does it involve a similar transformation?
It does. They use a similar diagonalization strategy, but this time they introduce a new variable, BI, which is related to the original susceptance matrix, BI.
Okay.
This is shown in equation 30.
All right, and I'm guessing they'll eventually switch to the S parameter representation, just like before.
You're catching on. But first, they introduce Ri and RIT in equations 34 and 35.
Okay.
And then using R, which is defined in equation 38, they finally express the optimization problem in its final form using those S parameters.
I see. A familiar pattern.
Simplify, transform, optimize, and transform back.
Right. Now, what's the key to achieving the optimal channel gain in this tree-connected case?
Well, a specific condition needs to be met, which is expressed in equation 41.
Okay.
It essentially says that for optimal performance, the transformed channel vectors, RI and I, should be related through the unitary matrix with a phase shift captured by a jur.
Lots of symbols there.
Yes, but the takeaway is that it's about aligning those vectors.
I see. To maximize the signal flow.
Precisely. By substituting those expressions, they arrive at equation 46.
Mm-hmm.
And this is a system of linear equations that need to be solved to find the optimal susceptance matrix BI.
So finding the values in BI that satisfy those equations will give us the optimal settings for the tree-connected RIS.
You got it. And luckily, this system of equations usually has a unique solution that we can find using existing algorithms.
Oh, good news. But how do we know that this solution for the tree-connected RIS will actually achieve the same channel gain upper bound as the fully connected one?
That's a great question, and that's where equation 50 comes in.
Okay.
It demonstrates that the maximum achievable channel gain for the tree-connected RIS is actually identical to that upper bound we derived for the fully connected RIS.
So even though it's a simpler structure, when optimized properly, it can perform just as well.
Exactly. It shows the potential of tree-connected RIS as a more efficient option, especially when complexity is a concern.
Very cool. Okay, we've seen how they optimize both fully connected and tree-connected RIS.
Right.
Taking mutual coupling into account. What's next?
Now we're going to dive into how the channel gain actually scales with the number of RIS elements.
Okay.
And this is where we really start to see the impact of mutual coupling.
I'm ready. Let's go.
All right. So to understand how this channel gain scales with the number of elements in the RIS, we're going to focus on a situation where the direct link between the transmitter and the receiver, it's blocked.
So we're basically removing that direct path.
Exactly.
Making it more challenging.
Yeah, making the RIS do all the work.
Okay, that makes sense. Anything else we're assuming here?
Yeah, we'll assume the channels ZRI and ZIT, they follow these independent Rayleigh distributions.
Okay.
Which is pretty common in wireless channels when you've got a lot of scattering.
Right. Signals bouncing around everywhere.
Exactly. Now, for this analysis, we're mostly going to be using the Z-parameter representation.
Okay.
But don't worry, the conclusions we draw, they apply to the Y-parameter model, too.
Good to know. Good to know.
Because they're really just two sides of the same coin.
Right. Different ways of looking at the same thing.
Exactly. So how do we actually figure out these scaling laws?
Yeah, that's the big question.
Right. So equation 51, that expresses the achievable channel gain with mutual coupling, taking into account that blocked direct link. But to understand how it behaves on average, we need to take the expectation of that, which gives us equation 52.
Oh boy, that equation looks intimidating.
It's a bit of a mouthful, I know.
Yeah.
But we can break it down, right?
Okay.
The key is to look at each expectation term separately.
Right. Divide and conquer.
Exactly. So equation 53, that focuses on the first term, which involves the interaction between those channels and the inverse of the real part of the impedance matrix.
Lots of matrix math there.
Yeah, it gets a bit complex, but we can simplify it using some properties of trace and expectation.
Okay.
And that brings us to equation 57, which expresses the first term as a product of the channel gains and the trace of the squared inverse of the real part of the impedance matrix.
So both the signal strength and the structure of the impedance matrix, which is affected by the mutual coupling.
Right.
They both play a role in the average channel gain.
Exactly. They're all connected.
Okay, that makes sense. What about the second term?
Well, equations 58 through 61, they go through a similar process to analyze that second expectation term.
Okay.
And we end up with equation 62, which, again, highlights the relationship between those channel gains and the structure of that impedance matrix.
So a similar approach for that second term.
Right. Same idea.
What about the rest of the terms? Are they handled the same way?
We can apply the same strategy for the third term, leading to equation 63.
Okay.
But the fourth term, that one's a bit trickier.
Okay. How so?
For that one, we need to use something called the eigenvalue decomposition of the matrix.
Eigenvalue decomposition. All right. Sounds complicated.
It's basically breaking the matrix down into its fundamental components.
Okay, so we can analyze it piece by piece.
Exactly. This decomposition, along with some properties of Rayleigh distributions, and something called the central limit theorem.
Okay.
It helps us get to equation 64, which is a much nicer expression for that fourth term.
So different tools for different terms.
Right, got to use the right tool for the job.
Makes sense. Now, the remaining two terms, they introduce this concept of channel hardening.
Yes, channel hardening.
And what is that exactly?
So it's this phenomenon that happens in large antenna systems, where the variance of the channel gain actually decreases as the number of antennas increases.
So with more antennas, the channel becomes more predictable.
Exactly, less random.
Interesting.
So in our case, with more RIS elements, those last two terms, they become more stable.
Less random.
Right, which means we can approximate them as deterministic values.
Okay, see.
This is shown in equations 70 and 71.
So we're simplifying those last two terms based on this channel hardening effect.
Precisely.
All right. So are we finally ready to put everything together?
We are. We've analyzed all the individual terms, so we can combine them back into equation 52. And that gives us equation 74, which is the scaling law for the average channel gain.
With mutual coupling, right?
Yes, under Rayleigh fading.
Okay, so that equation tells us how the average channel gain changes as we add more and more elements to the RIS.
Exactly.
Taking that mutual coupling into account.
Precisely. But to really see the impact of mutual coupling, we need to compare this to what happens without mutual coupling.
Right. Got to have a baseline.
Exactly. So we go back to equation 51, and we imagine a simplified case where the impedance matrix is diagonal.
So there are no interactions between the elements.
Right. Each element is doing its own thing.
Okay, I see. So that simplifies the impedance matrix quite a bit.
It does. The real part of the impedance matrix becomes a single value, representing the self-impedance of the RIS antennas.
Okay.
And plugging that into equation 51, that gives us equation 75, which is the achievable channel gain without any mutual coupling.
Right. And then we go through that same process of analyzing expectations to get the scaling law for this case.
Exactly. Same idea as before.
Analyze each term.
Right.
Use those Rayleigh distributions, the central limit theorem, and we end up with equation 87, which describes how the average channel gain scales with the number of elements when there's no mutual coupling.
You got it. Now we have two scaling laws to compare.
Right. One with mutual coupling and one without.
Exactly. So what do we learn by comparing them?
Yeah, that's the exciting part, right?
It is. So in both cases, the average channel gain increases as we add more RIS elements.
Okay, that makes sense.
Which is what we'd expect, right?
Yeah, more elements, more gain.
But the mutual coupling, it adds a whole new layer of complexity to that relationship.
So it's not just a simple linear increase anymore.
Right, it's more nuanced than that.
Okay, I see. So the question is, does this extra complexity from mutual coupling help or hurt the channel gain?
That is the question.
It can't be a simple answer, right?
You're right. It depends.
Oh,
well, to answer that, we need some more powerful mathematical tools.
Oh, boy, what kind of tools?
Specifically, matrix inequalities.
Okay, right.
So there are these two lemmas in the paper, lemma 1 and lemma 2. And they provide these really powerful tools for comparing trace terms that involve these positive definite matrices.
Okay, so these lemmas are like the key to unlocking the answer.
Exactly. They help us understand how transforming the impedance matrix affects the channel gain.
I see. So they're essential for proving that mutual coupling can actually be a good thing.
You got it. Right. So these lemmas, they're like building blocks leading to a pretty important conclusion.
Okay, so they're setting the stage for this
indeed.
big reveal.
Right. But first, let's break down lemma 1 a bit.
Okay, sounds good.
So it basically says that for any positive definite matrix A, the trace of A is always greater than or equal to the sum of the diagonal elements of A.
So we're talking about a specific type of matrix here.
Right, a positive definite matrix.
And this lemma tells us something about the relationship between its trace and its diagonal element.
Exactly, how they're connected.
Gotcha. So just to clarify, the trace of a matrix, that's just adding up all the elements on the main diagonal, right?
You got it.
Okay.
So what this lemma is saying is that for these positive definite matrices, the trace is always at least as big as just adding up those diagonal elements individually.
I see. So even though some of the off-diagonal elements might be negative, the fact that the matrix is positive, definite guarantees that the overall trace will be greater than or equal to the sum of just those diagonal elements.
Exactly. It's like a lower bound.
Right, a minimum value.
And this seemingly simple fact, it actually has some pretty big implications.
Okay, I'm intrigued. Now, what about lemma 2? How does that one work?
So lemma 2, that one's a bit more involved. It brings in another matrix.
Okay.
It says that for any positive definite matrix A and any invertible matrix B, the trace of the product BA, B transpose is always greater than or equal to the trace of A divided by the trace of B, B transpose.
Okay, we're definitely stepping up the complexity here.
Haha, a bit, but it's worth it.
All right, I'm following along.
So now we're looking at the trace of a product of matrices.
Right, BA, B transpose.
Yes, and we're relating it to the traces of the individual matrices, A and B, B transpose.
Okay, I see. And why is this lemma so powerful?
Well, it lets us compare the trace of a transformed matrix, that BAB transpose, with the trace of the original matrix, A.
So we can see how transforming a matrix affects its trace.
Exactly. And this is really helpful when we're trying to analyze the impact of those transformations we made to the impedance matrix.
Right, back in the optimization problem.
Precisely. It helps connect the dots.
Okay, I'm starting to see the bigger picture here. But how do these lemmas specifically lead us to the conclusion that mutual coupling is actually beneficial?
That's where proposition 2 comes in.
Okay, the big reveal.
Yeah, this is the main result.
Right.
And it uses lemmas 1 and 2 to show that under certain conditions, the average channel gain with mutual coupling, it's always greater than or equal to the average channel gain without mutual coupling.
So those lemmas provide the mathematical foundation.
They do.
For proving that counterintuitive result. That mutual coupling can actually be a good thing.
Right. It's not always the enemy.
It's amazing how they use those lemmas to rigorously show that mutual coupling. When we account for it in the optimization, it doesn't hurt the performance and it can actually make it better.
It's all about understanding how to use it to our advantage.
Right, turning a potential problem into a solution.
Exactly.
Well, this has been an incredible deep dive, to say the least.
It has.
We started with the basics of BD-RIS and mutual coupling, and we went all the way to these advanced mathematical analyses.
And simulations.
Right. And we even uncovered this surprising result.
Yeah, it's pretty cool.
That mutual coupling, when harnessed correctly, can actually be our friend.
It's a reminder to always question our assumptions.
Absolutely. It's been a pleasure exploring this with you, and I hope our listeners are walking away with a new perspective on the challenges they might face in their own fields.
Me too. Sometimes the most innovative solutions come from embracing the unexpected.
Couldn't have said it better myself. Until next time. Keep those minds curious, and remember, sometimes the things we try to eliminate might actually hold the key to breakthroughs we haven't even imagined yet.
Absolutely.